All right, everyone. It's 11:30, so we can look at the solutions and the answers to the questions in the workshop problem. Right. So the first one is all about free body diagrams and translating the free body diagram into Newton's second law of motion. So the forces are already drawn, meaning the free body diagram is actually given already, and we just need to do to use those forces to write down Newton's second law of motion. So let's do the first one. Right, so the first one, you have a normal force that's upwards and a downward weight force, weight being mass times gravitational acceleration. So this mg is the weight force. We'll use again the convention that upwards is positive, to the right is positive, downwards negative, and to the left is negative. Right, so you can see you can see that the forces are only just along the vertical axis. So you're actually just getting the net force along the y, and that's equal to the mass times acceleration along the y. Okay, so looking at the forces, you have a normal force that's upward, so it should be positive Fn, and a weight force that's negative, so that should be a minus W. And you have mass times acceleration along the y. Right, so we've just expanded net force on the left side of the equation, and the right side of the equation is still just mass times acceleration along the y. Right, but if you notice the diagram, if you look at the relative lengths of the normal force and weight force arrows in the diagram, they're more or less the same length. So we can say that they're opposing each other and there's no motion. The box is just sitting there. So the acceleration along the y is equal to 0. Acceleration along the y is equal to 0. So mass times 0 should give you 0 on the right-hand side of the equation, and you still have normal force minus the weight force on the left-hand side. Okay, so you can leave your answer as like this, or you can also say that the normal force is equal to the weight force for the first case. All right. Okay, for the second scenario, we have 3 forces now. Still, you have the normal force and the weight force, but there's a push force that's downwards and 40 newtons. So we do again net force along the y, because all the forces are shown to be along the y. You have the usual normal force that's positive, the weight force that's negative, the same as in the first question, but you have this additional 40 newtons that is downwards. So that will be a minus 40 newtons. Okay, that will be the net force, left-hand side of Newton's second law of motion. The right-hand side is mass times acceleration along the y. Let me just put some more space here. Move. Okay. Oh. Sorry about that. Let me just try to, how do you remove this? Go away. I want to remove this. Yeah. Right, so that's for just There you go. That's what I wanted to do, to have space for B. Right, so you have normal force minus the weight force minus 40 newtons. That's equal to mass times acceleration along the y, because F net along the y equals mass times acceleration along the y. Okay, so again, if you look at the relative sizes of the force vectors along the y, if you try to combine the lengths of the 40 Newton force and the weight force, it's roughly the same length as the normal force. And so you have these counteracting forces that will give you zero acceleration along the y. In short, the object still remains at rest in this case. So the acceleration along the y is zero, and anything you multiply with zero is zero. So you have on the left-hand side of Newton's second law, you still have normal force minus the weight force minus 40 newtons. Yeah, I'll just remove that so that it's less cluttered, is equal to zero. You can leave your answer as that, because that's already Newton's second law of motion expanded to include the net forces. Right, so for the next question, you, instead of pushing downwards, there's a hand that's pulling the package upwards. So you still have the usual normal force and weight force as in the first scenario, but the additional 40 Newton force is now directed upwards. So following the same trend that we've been doing, net force along the y is equal to mass times acceleration along the y. You still have the upwards normal force, positive normal force, minus weight force because it's downwards, and then you have this upward 14 Newton pull. Comparing the sizes again, the combined length of the 14 Newton and the normal force is similar, is the same, more or less the same as the length of the weight force that's downwards. And there's no indication of movement or acceleration for the box. So we can say here that the acceleration along the y is equal to zero, again, in this case. And so you'll have normal force minus weight force plus the 40 Newton pull force is equal to zero. And then the last case is where you have acceleration. So the box has finally been lifted. There's no more support force. Therefore, the forces given are just the weight force and the pulling force, with the explicit indication that the acceleration is upwards. Right, so you still do Newton's second law of motion along the y because the forces are still acting along the vertical. You have two forces only in this case, the weight force and the upward pull force. So you have the pull force is positive and the weight force is negative because that's downwards. And you have mass times acceleration along the y. Acceleration along the y is not zero. Okay, it's actually not given. It's one of the things we need to find in question C. So you can leave your equation as this, or you can substitute the numbers and put, if you want, you can substitute the numbers and put the values for the pulling force and the weight force because those are given. I won't do that anymore because you can just, yep, so the pull force is 100 newtons and 98 newtons downwards. 100 minus 98 for the weight force is mass times acceleration along the y. All right, so any question about the writing down Newton's second law of motion using the free body diagrams that are given? No. All right, so the next question, using the information in the last diagram, what is the mass of the box? So the last diagram shows you that the weight force is equal to 98 newtons, right? So the weight force, it's the downward force, that's 98 newtons. And it also shows you that the weight force is equal to mass times gravitational acceleration, which we also know from our lecture. Right, so weight force is equal to mass times gravitational acceleration. We want to find the mass. The mass is tied to G via multiplication sign. So to isolate mass, we have to divide both sides with G, so that G divided by G is equal to 1, and we get rid of G on the right-hand side. So your mass will just be equal to the weight force, which is given, 98 newtons divided by 9.8 meters per second squared. So that will be a mass of 10 kgs. Right. Is that okay? Or are there any questions? Yep. Next, what is the acceleration in the last diagram? And we sort of started to work towards the acceleration already when we've written down Newton's second law of motion along the y. Yeah, we have pull force minus the weight force is equal to mass times acceleration along the y. We're given the pull force. The pull force is 100 newtons upwards, so that's positive, and the weight force is 98 newtons downwards, so that's minus 98. And that's equal to mass times acceleration along the y. So again, we need to divide both sides with mass to get rid of mass and isolate the acceleration along the y. So, and the mass, we've solved that from the previous question. So let me just substitute that now. 10 times acceleration along the y. So dividing both sides by 10, 10 divided by 10 is equal to 1. And so you're just left with acceleration along the y on the right-hand side. So acceleration along the y is 100 minus 98, which is 2 divided by 10, 0.2 meters per second squared. All right. Okay, and then last question, determine the normal force in the remaining 3 situations. So we just have the normal force. In the first one, we already found that to be equal to the weight force, so we'll not do that again. So in the first one, when we wrote down Newton's second law of motion, we already determined that the normal force is equal to the weight force. So let's do now the second scenario, this one with the hand that's pushing down on the box. We've written down Newton's second law of motion as this. Fn minus W minus 40 is equal to 0. So let me write that down. Fn minus W minus 40 is equal to 0. This is for the second scenario in the figure. Right, so we want to find the normal force. That means we need to get rid of weight force and 40 on the left-hand side of the equation to isolate Fn. So we do the reverse operation. We're subtracting with weight and minus 40, so we need to add weight, and we need to add 40 on the left-hand side so that we get rid of weight and 40, but we also have to do that on the right-hand side. Whatever you do on the left side, you have to do on the right side. And therefore, normal force is equal to, the weight force is given to be 98, plus the pull force is 40. So you have 138 newtons for the normal force. And then the third scenario, you have Fn minus weight, but this time you're pulling upwards. So instead of a minus 40, you have a plus 40 in this case, and that's equal to 0. Yeah, that was the equation that we wrote down for the third case using Newton's second law of motion. So we're just using that and manipulating that to isolate Fn. So again, we need to get rid of weight. That's a minus weight. So you have to plus weight on the left side, and then you have a plus 40. So to get rid of that, you need to do a minus 40 on the left side. But you have to do whatever you did on the left side, you have to do that on the right side as well. So you have normal force is equal to weight plus 40. The weight is given to be 98 newtons. Oh, sorry, minus 40. That should be minus 40. The weight is given to be 98 newtons, and that's minus 40. So you have 58 newtons for the normal force in that case. All right. Okay. Any question about that, or are we okay with question number 1? And can we move on to question number 2? Right. Okay. Thanks for the thumbs up. We'll go to question number 2. You have a bucket that's being pulled straight up by a string at a constant speed. Okay, constant speed meaning acceleration is equal to 0, and then it's being pulled by a rope. Okay, so to draw the scenario, draw the free body diagram first. You have this bucket. Anything that has mass will always have weight that's directed downwards, and then it's being pulled by a string directly upwards. So you have a tension force that's upwards. It explicitly says that speed is constant and it's in the same direction, so acceleration is 0. Roughly the size of your tension and weight vector should be the same, and you can sort of see that the tension should be equal to the weight force, right? So you can go through the whole net force of is equal to mass times acceleration, and you'll have tension minus weight is equal to mass times acceleration. Acceleration is 0. Tension minus weight is 0. So tension is equal to weight. So you can go through the Newton's second law of motion, analyzing the equation, or you can just intuitively say that the tension should balance out the weight force, and so the tension should be equal to the weight force because acceleration is equal to 0. And that's also a valid argument. So your tension is equal to, so recall that weight is equal to mass times gravitational acceleration. The mass is given to be 6 kgs. Gravitational acceleration is constant, 9.8 meters per second squared. So you have a tension force of 58.8 newtons, or rounded to about 59 newtons for 2 significant figures. Okay, are we good with that and move on to the next question, or are there any questions? Yep, good, cool. Right, here at a certain point, the speed of the bucket changes. It's now moving upwards at a constant acceleration of 3 meters per second squared. So it's no longer 0 acceleration. It's already a certain number of acceleration. So in this case, when the acceleration is not 0, you have no choice but to go through Newton's second law of motion, which we already did in the first case here. So you have tension minus weight is equal to mass times acceleration along the y. Okay, so you can no longer use the argument that the tension is equal to the weight force in this case, because acceleration is not 0 in this case. Right. So to find the tension, you need to rearrange this equation to get rid of the weight force. It's tied to the tension via a minus sign, a subtraction. So you need to do the reverse operation of a subtraction, which is the addition of weight on the left side to get rid of weight. But you also have to do that on the right side. So you need to add weight to the right side as well. Right. Essentially, you have tension is equal to mass times acceleration along the y, plus the weight force, which is mass times gravitational acceleration. Everything's given, so the bucket is 6 kilograms. Multiply that with the acceleration along the y is given to be 3 meters per second squared. So it's not 9.8 meters per second squared that you're multiplying to the mass in Newton's second law of motion. It's the actual acceleration of the object, which is 3 meters per second squared, as given in the problem, right? And then for the weight force, that's when you need the 9.8 meters per second squared being multiplied with the mass. Okay, so you can do the calculation. Sorry, I'll just substitute the value of the mass, which is 6. You can do the calculation and end up with 76.8 newtons, or that's rounded to 77 newtons for 2 significant figures. All right. Are we good with that, or are there any questions? Can we move on to question number 3? All right, good. Here, it's an elevator scenario. You have a woman in an elevator, and then there are different, so the acceleration is given, it's 1.5 meters per second squared, and the elevator is going down. Because she enters the 3rd floor and she leaves at the ground floor. So it's not explicitly stated, but you can intuit that the elevator will go down, right? So the acceleration should be downwards in this case. So this is the figure here, but the first step is to draw your free body diagram representing the woman as just a dot there. We know, again, the easiest force will be the weight force. Anything that has mass will have weight, and weight is always downwards. And then you have the floor that's supporting the woman, and the floor is horizontal, so you have this normal force that's directed upwards. Okay, I'm drawing the normal force to be a little bit smaller than the weight force because the problem explicitly says that there's an acceleration that's downwards, 1.5 meters per second squared, but that's a downward acceleration. So I'll put a negative 1.5 meters per second squared. So the negative sign here gives me the direction that's downwards. Right, so you have your free body diagram and sort of you've illustrated what's going on. Let's go to the first question. What's the normal force or the support force acting on the woman as the elevator accelerates, as the elevator is going down, right? So you write down Newton's second law of motion, net force along the y. Okay, all your forces are just along the vertical, so you're getting the y component. I mean, you're just getting, using Newton's second law of motion along the y. Net force along the y is equal to mass times acceleration. There are 2 forces along the y: the positive normal force because it's upwards, and the negative weight force because it's downwards. Right, so that's the left-hand side of Newton's second law of motion. The right-hand side is mass times acceleration along the y. It's not 0, okay, because the problem explicitly says acceleration is negative 1.5 meters per second squared. So normal force is not equal to weight force, right? You cannot use the argument that the normal force is equal to weight force. Instead, you have to rearrange this equation to isolate the normal force. And we did that again earlier. We already did that earlier, but I'll just do that again. Get rid of weight by adding weight on the left-hand side, but you also have to add weight on the right-hand side so that your normal force is equal to mass times acceleration of the woman plus the weight of the woman, weight force. We were given the mass. 52 kilograms. Okay. Multiply that with the acceleration, it should be negative 1.5. Right? Because the acceleration is downwards. So the mass of the woman should be multiplied with negative 1.5 meters per second squared. That's the mass times acceleration part of the equation. And then you need to add the weight. And weight is equal to mass times gravitational acceleration. The mass is 52 kilograms times 9.8. And you work that out using your calculator, you'll have 431.6 newtons. Are we okay with that? And move on to the next question. Right. So the next question, the elevator moves at constant speed. So acceleration is equal to 0. Looking at your free body diagram, you only have the normal force and the weight force there. Okay, so then you can use the argument that since the acceleration is equal to 0, then the upward force should cancel out the downward force. And here, you know that the normal force should be equal to the weight force. And the weight force is the mass times the gravitational acceleration, okay, which is 509.6 newtons, or that's about 510 newtons for the normal force, right? So yeah, if the acceleration is 0, it's sort of simpler, a bit simpler than when there is acceleration present, okay? And then the next question, the elevator slows down. Okay, so something will happen to the acceleration when the elevator slows down. Because what happens when the elevator slows down, that means the final speed is less than the initial speed, right? And we know that acceleration is the change in velocity over time. It's in the same direction. So the direction's the same. It's just the speed that's changing and giving you this acceleration. So acceleration will be the final minus the initial speed divided by time if you're getting the magnitude of the acceleration. But since your elevator is slowing down, the final speed will be less than the initial speed. That means the acceleration, the value of the acceleration you'll get will be negative, right? Negative value for the acceleration, but at the same time, the direction, yeah. So the direction is downwards. Is also negative. A negative number you multiply with a negative will give you a positive. Overall, acceleration is positive. So how the equation changes, yeah, your equation will still be the same because it's still the same forces involved. It's still normal force and the weight force that are acting on the elevator. So it's still the same net force. It's still the same equation for Newton's second law of motion. Right? So it's still normal force minus weight force is equal to mass times acceleration along the y, which we rearranged earlier as mass times acceleration plus weight force. But here, the only thing that will change will be what you will put as a number in the acceleration. So here that will be 52 kilograms for the mass of the woman times, this time it will be a plus 1.5 meters per second squared. Okay? Because the elevator is slowing down, the magnitude of acceleration will be negative, but then that cancels out the negative direction and you'll have a positive acceleration. Yeah. And then the usual weight force, 52 times 9.8 meters per second squared. That will give you a normal force of 587.6 newtons, rounded to two significant figures, 588 newtons. All right. Okay, and then the last one. So do your answers depend on whether the elevator is moving up or down? Okay, it's not really moving up or down. It depends on whether the acceleration is positive or negative. So no, it depends on whether acceleration is positive or negative. We've seen in the example in the question C, we've seen that the acceleration can be positive even if the elevator is moving downwards. Okay? If the elevator is moving downwards, but it's slowing down, then that has an overall positive acceleration. And it's really just whether the acceleration is positive or negative that affects the results for the normal force, rather than whether the elevator is moving up or down. All right. Cool. So that's the workshop for today. Any questions about the workshop or the lecture or anything else? Right. Okay, so I don't see questions in the chat box and it's 12. Anyway, we'll have the review workshop at 1. So if you come up with any questions, you can ask those during the review workshop anyway. But I guess we can wrap it up and then we can have lunch and hopefully see you at 1. All right, thanks everyone. Stop the recording.